Thank you. And like everyone else, I'd like to thank the organizers. It's been a great conference, and I'm going to be thinking about a lot of the talks for quite a while. And this talk is about computing periodic conformal mappings, one of which is illustrated on this title slide. And I don't really need to justify to this audience why we should study conformal maps. They're interesting and beautiful in their own right. But the reason one of the reasons why I find them so attractive is that they are very powerful for solving practical problems. So we've heard problems this week in fluid dynamics, electromagnetism, and computation. So this is my view of conformal mappings, that we might have some problem in a domain or a geometry that's very difficult to solve. You may be interested in, for example, the flow past a cow, as many people are interested in. And the conformal mappings allow us to relate this cow with its complicated geometry, including these hooves, horns, and ears. It allows us to relate this complicated space to more simple and more familiar geometry. So now we can solve our fluid problem, our solid mechanics problem, our computational problem in the spherical cow domain, and then map that back to our physical or our target domain of interest. And that allows us to speed up computations and gives us more physical insight and really makes a lot of these problems far simpler. And of course, all conformal mappings that we talk about really are just two-dimensional. This was just a 3D example, but I couldn't resist putting a spherical cow in this talk.
Basically, we're talking about super efficient diagrams.
So we're interested in periodic conformal mappings, and there are three possible types of periodic mappings. You can have a bounded domain on both sides. So here, we always work in circular domains, not in landscapes like in the last talk. And we're mapping a circular domain to a periodic polygonal domain in this talk. And the red boundary circle is going to be mapped here to the top boundary, and the blue boundary circle is going to be mapped to the bottom boundary. And this conformal mapping is just given by this really simple relation, 1 over 2 pi I times log of zeta. And because there's this branch point at 0 in the circular domain, that results in a branch cut along here, for example, and that results in these two period windows on either side of the boundary. So as we wind around this red circle or this blue circle, we're going to add 2 pi I, well, divided by 2 pi I, to our function. And that's how it's periodic, because this branch cut is multi-valued. So multiple points, or the same point in the circular domain, is mapped to infinitely many points in this polygonal domain. But if instead we don't have this interior circle, then our branch point is just somewhere inside this circular domain. And a result of that is that the ensuing target domain is unbounded in one direction, because there's this one point in our circular domain, a infinity, that is mapped to infinity, because it scales like log zeta minus a infinity there. So this domain is now unbounded in one direction. And in the other case, when we have two interior branch points like this, now our target domain is unbounded in both directions, because going to this point in the zeta domain, for example, goes up here in the z domain, and going to this point in the zeta domain goes down here in the z domain. And here is a canonical or a typical type of mapping. And these are the mappings that we're really focusing on today, because they haven't received that much attention previously, and they also have some quite interesting physical implications when we study fluid problems. So as a reminder, I've got, hopefully it's still here, just an illustration of the type of geometry that we're working with. So we're mapping a single circle to a periodic array of polygons. These are the same polygon, but they might not look like it. And we have this branch cut connecting our two preimages of infinity, one which goes up here and one which goes down here. And the problem we're trying to solve in this talk is to find f. F is the function that relates our zeta domain to our z domain. And whilst the Riemann mapping theorem guarantees that f exists, it's very difficult to construct it in practice, and that is the target of this talk, both constructing f and representing it efficiently. And the typical tool for constructing conformal mappings is the Schwarz Christoffel formula, which provides a constructive procedure for computing these mappings. And if we're not familiar with the Schwarz Christoffel formula, it is a formula that gives us the conformal map from a circular domain or another canonical domain, like the upper half plane, to a polygon. And here it's just a square. And because we're mapping from the interior, this white domain, to the exterior of this polygonal domain, that means that we have to have a singularity inside our circular domain. So in this case, it's a simple pole at a infinity which is mapped to infinity in the Z domain. And this has been known for over 150 years, at least in the simply connected case. But in order to really know the Schwarz Christoffel formula, we need to determine something called the parameters. And these are just the points on this circle that are mapped to the vertices of this square. And it's not at all obvious which point on the circle is mapped to the vertices of the square. And Nick Treveth and Terry Driscoll and many other collaborators worked for quite a while on this parameter problem and developed a range of numerical techniques which are now compressed into the Schwarz Christoffel toolbox, which you can download into MATLAB, and then you can compute the mapping for a polygon with hundreds of sides very quickly. And a major theoretical advancement came in the early 2000s when two groups of researchers, Darren Crowdy at Imperial and Tom DeLillo and his collaborators at Wichita State, derived the multiply connected Schwarz Christoffel formula. So now, instead of just having one disk mapped to one polygon, they could now compute the mappings for multiple disks mapped to multiple polygons. And actually, these formulations were valid for any connectivity, so not just singly connected or triply connected in this case, but any number of objects per period window. And then earlier this year, we derived the periodic Schwarz Christoffel formula. So not only do we have multiply connected domains, but the domain is also periodic. So as you wind around this branch cut, you're adding the period to your mapping each time, and winding around this branch cut takes you across into different period windows. And I was surprised to learn that this was one of the cover articles of Proceedings of the Royal Society in the August edition, although I only just found out this week when Anastasia told me about it. But you can read the full article there. So this is roughly how we constructed the Schwarz Christoffel formula for the multiply connected periodic domain. The key is really to take something called a Cayley type map. And basically, with a Schwarz Christoffel formula, you want the derivative of the mapping to take piecewise constant argument. And that's fine in the simply connected case, but when you have multiple circles, how do you have piecewise constant argument on one circle without screwing up the argument on the other circles? And the technique is to take something called a Cayley type map. So for each circular domain, like this quadruply connected example, we can take a Cayley type map that maps one circle, like this red one, to the real axis, and then every other circle to a line of constant argument. And that's great because now we can exponentiate that mapping to achieve the required angle that we want. So here we've just got a right angle, and we've done the appropriate exponentiation. But because all of the other circles were mapped to these lines of piecewise constant argument, exponentiating them doesn't, well, it changes their argument, but it's still piecewise constant. So now the approach is basically to take products of all these kind of angles that we want, and it's going to satisfy the this condition at the top, and also have the appropriate branch points. And taking products over all of those gives you the final formula. There are a couple of details in this SP here, and that basically accounts for the periodicity. So these beta kj's are the angles, like here, you've got a right angle. And these AKs are the parameters, so these are the points that are mapped to the vertices. So we don't know those a priori, but we'll determine them with a numerical scheme. And this omega here is the Schottky-Klein prime function, which has been mentioned in a couple of talks today. And if you don't know about it, it's the fundamental tool for working with multiply connected domains. So it was discovered, or at least recorded by Baker, who you'll notice is not called Schottky nor Klein, but then really rediscovered by Darren Crowdy and made accessible and applicable to problems in fluid dynamics in the early 2000s. And basically, every circular domain, such as this triply connected domain on the right, has an associated prime function. So here are a few examples. So in the simply connected case, when we have the unit disk, the prime function is just the difference of its arguments, like this. So that's the simplest case, just the difference of its arguments. But if we take out another disk, now we're working with the annulus, where the interior disk is of radius q. And this blue guy is always the unit disk. So now the prime function is this product. But in the more general multiply connected case, again, triply connected, the prime function is given by this quite complicated product. We suppress the dependence of the prime function on the radii in the sense of these circles, just for notational convenience. And all those parameters live inside these thetas. I won't go into the details of those. But you should never use this formula to actually compute the prime function numerically, because I'm not certain it's proven for every choice of circular domain this converges. Instead, we should use this algorithm by Crowdy and collaborators, which is available on GitHub. Okay. So here's an example of a periodic conformal mapping that we found using the Schwarz Christoffel formula. Actually, this was known before, but it wasn't really seen as a Schwarz Christoffel formula, but this is obviously a polygonal domain. And you can basically write the formula in this format. And again, winding around these branch points adds 2 pi to the argument every time, or 1 over 2 pi, some real constant goes from there to there. So this point here is mapped up here, and then this point here is mapped down here. And if we take these 2 branch points to be closer and closer to each other, then we're going to make the period larger and larger. So let's see what happens if we do that. So on the left-hand side, we're taking these branch points closer, and on the right-hand side, we're just plotting the effect of the conformal mapping under that parameterization. And you can see on the left-hand side, now these 2 branch points are basically on top of each other, and they're overlapping, or we say they've coalesced. And if you do L'Hopital's rule on this formula, then you just get the Joukowsky map back. So this original periodic mapping is really the periodic analog of the Joukowsky map. And we recover the Joukowsky map in the large period limit. And it's similar for the Schwarz Christoffel formula. We recovered the original Schwarz Christoffel when we take the period to be large, because I suppose that everything is periodic, just sometimes the period is infinity. So really those cases are a special case of our periodic mapping. Here are some other examples, because it's valid for any connectivity. I'm mainly showing simply connected examples. So here's a doubly connected example here. Then a triply connected and quadruply connected example here. And as I've mentioned, there's this issue of determining the parameters, so which points are mapped to the vertices. So where should we put these blue dots such that we get a square on the right-hand side? And we can show that there are as many variables as there are unknowns in this problem, in the multiply connected case. And I adapted the SC toolbox to compute the parameters in the periodic case. Hopefully that will be made public soon. There are quite a lot of details which have been worked on by various people, some of whom are here, to optimize this, because this is quite a difficult minimization problem. But it's really just based on what Toby Driscoll has done with the SC toolbox. Okay. But one of the issues with this mapping is that even if we've solved the parameters, and we know how to go, we know which points to map to the vertices, we don't really want to have to evaluate this map in its current form, because the Schwarz Christoffel formula really only gives us the derivative of the map, and then we're free to integrate that with whatever routine we want. And that can be very expensive, and especially in our case where we have this quite complicated branch structure, we don't want to use the integral form. Instead, what we can do is just evaluate this integral on the boundary, and then represent that function using, for example, rational function approximation. Because by the maximum value principle, if we can minimize the error on that boundary, then the error will be minimized inside the domain itself as well. So instead of integrating this formula throughout the entire domain, we'll just integrate it on the circular boundary, and then use that boundary correspondence function to represent the conformal mapping throughout the entire domain. And yeah, Abby Gopal and Nick Trevethan published this paper this year, which suggests this idea and implements it in the non-periodic case for simply connected domains. And we use the AAA algorithm to determine the parameters of the rational function. So I probably don't need to remind this audience of the AAA algorithm, but here it is anyway. So we represent the approximant in this barycentric form, and the problem is now to determine the support points, Zj, and the weights, Wj. And the nice thing about AAA is that it's very flexible with respect to the domain, so it doesn't have to be a real interval. It can be any complex domain, which is great for conformal maps. And the 2 main steps in AAA are the greedy selection of the support points to minimize the instability of the algorithm, and the weights are chosen via a least squares problem, and that's to make the approximant accurate. And AAA is implemented in ChebFun, which you can download there. Okay, so if we just try and represent the forward map using a rational function approximation, we run into a problem. So if we took this circular domain and tried to map it to this periodic domain using AAA, this is an example of the result. So these red dots represent the poles of the mapping, and the green dots represent the parameters, which we found using the Schwarz Christoffel toolbox. So these green dots are mapped to these green vertices. And what AAA has tried to do here is represent this branch cut, which is this blue dashed line, with a continuum of poles. Because really, that's what a branch cut is. It's just poles of infinitesimal strength summed up. And you can see the effect of the mapping is not very good because the AAA is putting these points inside the squares, whereas they should all be outside the square. So the way that we deal with this is by subtracting out that singularity, because in this case, we know the strength of the singularity and we know its location. Because we know the period of the domain, the coefficient of these logs must be the period divided by 2 pi I. Because then when you wind around that branch point, you're going to add the period to the argument, which is exactly what you want. And now we can approximate this remainder f using rational function approximation, particularly using AAA. And that is a way of accurately representing the branch points on the boundary and the singularities there. So here's an example. We map the unit disk with this branch cut to this array of L-shaped polygons, which is apparently quite a common test for people to do conformal mappings on. And you can see now none of the interior points, none of these blue dots are mapped to the interior, so it appears to be working. Here are a couple of other examples. So there's just a randomly generated polygon. And here is a much more challenging example where it's elongated. So we have this phenomenon of crowding, which has been mentioned several times today. And you can see that illustrated here. So you can barely see these green dots because they're basically on top of each other because this domain is being stretched out and the mapping wants to place these points as close to each other as possible. Okay. So we've done the forwards map, but very often we want to go backwards. We want to start in the polygonal domain and then go backwards into the circular domain. And the previous mapping was multi-valued. The same point was mapped to infinitely many different points. Then this mapping is now periodic. Infinitely many points are now mapped to the same point because, for example, this point is mapped to the same point as this point as this point. So now people would usually use a Newton iteration on the Schwarz Christoffel mapping to find the backwards map, but it's extremely expensive. Instead, we want to use rational function approximation to do the backwards mapping. And now our approximant takes this form. And in particular, R must be a periodic rational function. Because at the moment, AAA just works for these polynomial rational functions. I guess all rational functions are polynomial. But in our case, we want it to be periodic. So our approach here is to instead of just taking one support point, we want to take infinitely many support points that are each spaced with this particular period. So we express our rational approximant in this form. But this sum is just the partial fraction representation of cotangent. So we can actually represent the approximant in this quite concise form. And we can now apply a really similar procedure to AAA to find the weights and the support points. And then we find the poles and zeros by solving a generalized eigenvalue problem. So pretty similar to the original AAA algorithm. But how does it perform? So this is some data that is taken from the original AAA paper by Eugene Olivier and Nick Trevethan. So here we are approximating tan of beta z by sampling 1,000 points on the unit circle. And the circles represent periodic AAA, and the triangles represent original AAA. And it's for a range of frequencies. And you can see that the telling AAA the period improves the performance by quite a long way. So here it just needed three cotangents to get an accurate representation. We just send it to 10 to the minus 13 in this case, in terms of accuracy. And in every case, it outperforms the original AAA algorithm. But it should, because we told it extra information. So it'd be pretty bad if we told it extra information and it did worse. So this is quite reassuring that it did perform better with the extra information. And you might complain that this is a bad comparison because the unit disk will contain several period windows, or well, maybe hundreds of period windows of this function. So we've also compared it on just a unit interval. So this is e to the cosine of x, and we're just sampled on the interval 0 to 2 pi. And what we're seeing are the error curves. So here x is ranging between 0 and p, which is 2 pi, for original AAA and periodic AAA. And these m's correspond to the number of terms in our rational approximant. And you can see that after 10 iterations, periodic AAA has got down to 10 digits, whereas original AAA is still around 6 digits. So hopefully this is more evidence that periodic AAA it is more effective when we tell it the period, and it's a periodic function we're approximating. Okay, so now finally here are some illustrations of the periodic conformal map. So we're mapping these squares onto this circle, and here's a close-up. And you can see that exponential clustering of poles, which are represented in red, and they want to cluster as close to that corner as possible to try and represent the singularity there. And here's another example of an elongated region, and we didn't tell AAA the structure of the branches. It discovered this kind of intrinsic branch structure that runs along the center of this rectangle here. So that's very nice, and it goes onto this target domain here. Okay, so now we have the forwards and the backwards mappings going from circular domains to periodic polygonal domains. And in the remainder of this talk, I'm going to illustrate an example in fluid mechanics. So not many people realize, but the advection diffusion equation in a potential flow is an example of a conformally equivalent or conformally invariant problem. And the reason for that is basically that in both of these equations, every term in the equation has a nabla squared, basically. And because the Jacobian of the conformal mapping is of this nice form, those Jacobians will cancel out, and we can map this domain onto just a single circle and solve the problem there. And so in fluids, so the physics of the problem is that we have some flow coming into this grating. We have some concentration of maybe a chemical or a temperature that's prescribed on the boundary. And we say that concentration is 0 upstream. And we have a no-flux condition on the boundary of the circle. So our approach is to map this problem into the circular domain and then solve the problem there and then map it back into the physical domain of interest. So there are two things that we need to solve, given the conformal mapping. We need to solve for u, the velocity, and then we need to solve for c, which is the concentration. So this is how we solve for u. Some previous work that I did solved this problem for asymptotically thin objects, such as an aerofoil. But now with our conformal mapping, we can solve it for any geometry. So we want to solve our flow problem in the circular domain, and the conditions on W, the complex potential, are these. It has to be harmonic, it has to take constant imaginary value on the boundaries, which is the no-flux condition, and it has to have these particular log singularities at these pre-images, and that corresponds to what we call a uniform flow in the physical domain. So this is roughly how we construct the solution, which is exact and is also valid for any connectivity. Basically, we construct two new conformal mappings. You probably thought we were done with the mappings, but we have two new ones. I call them V and H. And basically, they map this circular domain to this periodic array of slits with constant imaginary value. And H is the same, except now the period is in the horizontal direction. So both V and H satisfy point 1 because they're conformal maps, they're harmonic, or they're analytic, I should say. And because these slits have constant imaginary value, they also satisfy 2. They take constant imaginary part on the boundaries. But the problem is that neither V nor H satisfy point 3. They don't have this prescribed log singularity behavior. But by taking real and linear combinations of H and V, we can satisfy 1, 2, and 3. So phi, sometimes called W, can be represented in this form. For any connectivity, for any period, for any angle of attack, any angle the flow is coming in at, this is the solution. And omega here, again, is the Schottky-Klein prime function. So this is quite a nice and very concise formula that contains quite a lot of information. So here are some visualizations of that. Because it's a multi-valued function, maybe the natural way to view it is on a Riemann surface, which is illustrated here. And here we've just illustrated that, that complex potential on a range of domains of different connectivity. And you can see this flow pattern seems to be valid for any connectivity. because it doesn't pass through any of the boundaries. Maybe it looks like it does here, but if you zoom in, you'd see that it actually goes around it. And here are some visualizations of that flow in the physical domain. So here we're calculating the flow past just some random blobs, and the flow is going from left to right, and this is the flow in the zeta plane. So physically, this corresponds to a source here and a sink here. So it's like we're injecting fluid at this guy and then it's sucking it out here. And in the physical domain, after that conformal mapping, that corresponds to injecting fluid at this side and then bringing fluid out in this side. And again, as you can see, it's valid for any connectivity. And we can also include other potential flow phenomena like point vortices and circulation. So now we've changed the circulation around these objects by placing a point vortex at this preimage of infinity. And the effect of that is to change the angle of the flow in the downstream region. So now you can see that it's going out at a different angle as to what it was before, even though the inlet angle is the same. And this is quite interesting physically, because if you just had an isolated aerofoil or blob or whatever, for any circulation in the far field, that will eventually, the flow will eventually decay back to unity. But here we can actually change the angle for any circulation because we have this array of objects. Okay, and now here finally is the result. I haven't gone into the details of how we solve the advection diffusion equation. That's just done using a numerical FEM method in the circular domain. But the nice thing is that that circular domain doesn't see any of these points of non-smoothness on this boundary because we've done the conformal mapping. And this is advection diffusion for a range of Peclet numbers. So the Peclet number represents the ratio of advection to diffusion. So in these low Peclet number regimes, diffusion is dominating, so this chemical is free to spread out. But when we crank up the strength of the fluid flow going in, now the Peclet number is high, and the chemical or temperature is restricted to these thin boundary layers that propagate downstream. And actually, in this case, these boundary layers do reach downstream infinity, whereas in the isolated case, they don't reach downstream infinity. So some quantity of this chemical or temperature is going to be convected all the way downstream at infinity. Okay, so these are the conclusions. We presented some new techniques for computing these conformal maps for periodic domains. We particularly focused on these polygonal domains. And the theoretical results we presented, like the Schwarz Christoffel and the potential flow problem, were all valid for arbitrary connectivities. And that's by virtue of the prime function, we can solve these for any connectivity. So two objects, 3 objects, 300 objects per period window. Theoretically, it's all the same. Computationally, we've only implemented these for simply connected geometries because it becomes significantly more complicated in the multiply connected case. And we adapted AAA to represent the mappings in both the backward case and the forwards case. Some future work, we heard about the Szego kernel yesterday for smooth boundaries. Maybe that can be adapted for these periodic domains. A couple of other things here, and maybe Lemming-Scatic domains as well is something I should be looking at. So thank you for listening. I'll be happy to take questions. Hi. Yeah.
Can you do this for periodic rectangular windows?
You mean doubly periodic? Yeah, I've been thinking about this a fair bit. I haven't seen any properly doubly periodic conformal maps. And actually, you do lose some of the physics if it's doubly periodic because you can't have any circulation around any objects. Because
for these advection diffusion problems, the cycle itself problem that people in the business really care about.
Yeah. So I don't know how you would do it with a conformal mapping, but the principle would hold if it exists. Yeah, but I don't know how to do it at the moment. Maybe actually Giovanni knows apparently.
You can use the secondary prime functions. Because I like to type of problem to listen to directions. So for the one to go vertically, you can use replace your primary prime function. The secondary prime function has to take care of this other boundary condition. So I think you can generalize this to take into account this periodic case.
Yeah, I hope so.
For Baddoo.
Yeah, yeah,
The theory of Baddoo, you have a wall.
yeah,
So it's periodic goes in the vertical direction.
yeah,
Because it's just reflected in
yeah.
periodic.
So I think. Yeah, yeah, or times a phase shift or something. Yeah, I'd love to know how to do that. I have no idea at the moment. Yeah. Hi.
Yeah, I'm wondering if you could have completely avoided integration on the boundary. In the following way. You have a formula for the what is called this centered, what is this, R of Z. You have a rational expression.
Yeah, yeah.
So why not take the derivative of that with respect to the parameter and match it with the derivative of the conformal map in order to find the location of Vj and use the greedy algorithm and whatsoever, and in which case you only need one constant at one point to figure out the rest of it. So that will avoid all this integration.
Yeah, it's true. So then you integrate the rational function, you mean?
You just need one point. So you have the greedy data. That is, you're looking to match that with the rational expression.
Yeah. But then you only get the derivative of the rational function,
Correct.
which will be rational as well.
Correct.
But then when you integrate that,
Particular form.
yeah.
So it's the derivative of whatever you have, and you look for matching that form.
Yeah, I could try that, yeah. But the integration, it's not very expensive doing the integration because it's just around one circle. Actually, we need to do it anyway to find the parameters. But, yeah.